Hey everyone, today I'm going to be showing you how every reaction is actually reversible. To show you what I mean, I'm going to start off with these two colorless solutions here. In this one, I have some thiocyanate ions, and in this one, I have some iron 3+ ions. Now when these two combine together, they make iron thiocyanate, which is a red color. So you can see when I combine them together, it gets kind of this orangish red color. But here's where it gets interesting. You might just assume that all of the iron reacted with the thiocyanate to form iron thiocyanate. But if there were no more of the reactants in here, then that would mean if I just add more of only one of the reactants, like iron, then it shouldn't react. Let me show you what I mean. So let's split this into two test tubes here. But let's add some iron drops to this. So you can see that just by adding more iron, it got darker. So this would lead you to believe that, okay, maybe the iron got all used up, and so we had to add more of it for the products to occur. But we have the same solution here. So in this one, I'll just add some more thiocyanate to it because we assumed that the iron got all used up. So here's a crystal of thiocyanate. And we can see that this turns it red too. So you can see that whether I added iron or thiocyanate, we got more of the products. Now what you just saw here is something called Le Chatelier's principle. For example, let's say we have a beaker of iron and thiocyanate mixed together, and each of these are represented by these white dots. So two white dots can combine together to form a red dot. And the red dot is iron thiocyanate. You can see that once the reaction starts, it doesn't just stay reacted, but the red dots are continually turning back into two white dots, and two white dots are continually forming red dots. Depending on the speed that the white dots react compared to the speed that the red dots split into two white dots, you can get a certain concentration of both red dots and white dots. You can see that on average, the number of red dots and white dots stays the same after a while. This is called equilibrium. So Le Chatelier's principle tells us that it wants to keep this same ratio of concentrations of both the red dots and the white dots. So if you start out with only white dots, it's going to push it to have more red dots. And likewise, if you start out with only red dots, it's going to push it to have more white dots. If you change the concentration of any of these dots, it's going to push it one way or the other. So what I can do is if I just take out some of the iron ions, it's going to push the products to want to go back to the reactants. So I'm going to do that by just adding in some sodium phosphate, and that'll react with the iron ions, and so it'll push the products to go back to the reactants, which should make it colorless. So in this case, we had too much product in there, and so it made the product do the reverse reaction and go back to the original iron ions and thiocyanate ions. So you can see with equilibriums like this, you can change everything by just changing the concentration of any of the reactants or products involved. So Le Chatelier's principle is easy to remember. If ever you have a reaction taking place, it's always going to form an equilibrium, where it gets to some concentration of the reactants and products. But if you ever add more reactants, it's going to push it to have more products. But the opposite is also true. If you have too much product, it's going to push it back towards the reactants. Now, Le Chatelier's principle can actually be pretty helpful in your everyday life. For example, let's say that you have some ice on your driveway that you want to melt. Well, you can wait for the sun to heat it up and turn the solid ice into liquid water, but that's going to take a little while. So as the sun slightly heats it up, some of that solid water is going to turn to liquid. So you reach an equilibrium between the solid water and liquid water. There's always some liquid water turning back to solid, and there's always some solid turning back to liquid. And this is an equilibrium. But you can mess up this equilibrium by reducing the concentration of the liquid water. So if you add some salt to that, that changes the concentration of the liquid water. So the solid water now wants to turn back into liquid water because we lowered the concentration of the liquid. So this is essentially what happens when you put salt on ice. It doesn't actually melt the ice, but it changes the equilibrium so it pushes the solid ice to become liquid. And it doesn't have to just be salt. You can actually add anything to it. Anything that lowers the concentration of liquid compared to the solid, it's going to make the solid want to turn to liquid. And this is called freezing point depression. What's interesting about Le Chatelier's principle is it depends on the fact that the reaction is reversible. So you may not think this applies to every reaction, but actually every reaction is reversible. Even some of the reactions that we don't think of as reversible, like combustion. For example, we know that ethanol burns, And the products are mostly carbon dioxide and water. The only reason that it keeps burning until the ethanol is gone is because we're continually removing the products of water and CO2 from the system. So we have a low concentration of products, so that makes it want to produce more products. But if we keep the products there, then we're actually going to end up with too many products and the reactants will stop reacting. But if I say that everything is reversible, why is it that in your chemistry class you're taught about reversible reactions and irreversible reactions? Well, that's because for a lot of reactions, the concentration of products that you would need to make the reverse reaction occur would have to be extremely high. Maybe it would even be larger than the entire universe that you'd need. But everything is still reversible. For every reaction, there's something called an equilibrium constant. And things that we call reversible usually have a small equilibrium constant, which means there's a good concentration of both products and reactants. And usually for reactions that we call irreversible, just means that they have a large equilibrium constant. But there's no such thing as an infinite equilibrium constant. So that even though it may be very high, that means that no matter what, there's always some concentration of products at some temperature and pressure that would make it so that the reversible process is always happening and you're not using up all of your reactants. Thanks for watching another episode of the Action Lab. I hope you enjoyed it. If you did, don't forget to subscribe if you haven't subscribed yet. And also check out theactionlab.com where we sell Action Lab experiment kits and other cool science gear there. And thanks for watching, and we'll see you next time.